Have you ever really stopped to think about what's happening inside your phone or your laptop? It's not magic, not at all. It's math. And today, we're going to open up the Electrical Engineer's Toolkit and show you the essential mathematical language that makes our entire electronic world tick. So let's just start with this one big question. How can a bunch of abstract equations, stuff on a blackboard, perfectly describe the actual electricity flowing through the device you are using to watch this right now? That connection, that incredible bridge between a pure idea and a physical reality, well, that's what we're here to explore. All right, here's our game plan. We're going to start with the fundamental language of electronics. Then we'll add 4 essential tools to our kit. One for things that wave and oscillate, another for things that grow or fade away, then a seriously cool secret weapon that combines the two, and finally, a master key for cracking open even the most complex signals. First things first, we need to learn the language. Before an engineer can even think about solving a problem, they have to be able to describe it, right? And in electrical engineering, that whole language is built on one single powerful idea. And that idea is the differential equation. Now, I know, the name sounds a little intimidating, but don't let it fool you. All it is an equation that describes how something is changing from one moment to the next. It's the language of motion, of change, and it's how we describe pretty much every physical system you can imagine. And this is what makes an engineer kind of like a fortune teller. They can look at a circuit and use a differential equation to describe how its voltage is changing in this very instant, and by solving that equation, they can predict exactly what it's going to be doing seconds or even hours from now. It's powerful stuff. Okay, so we've got the language down. Let's grab our first tool from the toolkit. This one is for anything that repeats, anything that waves, anything that oscillates. And for that, there are 2 functions that are the absolute rock stars, sine and cosine. You've definitely seen these beautiful flowing waves before. These aren't just some random shapes. They are nature's go-to pattern for anything that repeats, from the sound of a guitar string to the electricity in our walls. So why are these 2 so perfect for the job? Well, they've got this amazing set of properties. They're periodic, which just means they repeat the same pattern forever. They're bounded, so their values don't just fly off to infinity. They stay neatly between -1 and 1. They're continuous, so there are no sudden jumps or breaks. And maybe most importantly, the way they change is perfectly cyclic. The rate of change of a sine wave is just a cosine wave. It's an elegant, self-contained little system. And let's be clear, this isn't just theory. This is it. This is the math that describes alternating current, AC, the oscillating voltage coming out of every power outlet powering our entire modern world. It's literally sine and cosine waves. Okay, tool number 1 handles the waves. But what about things that don't repeat? Things that just grow or fade away. For that, we need to reach back into our toolkit. And here it is, the exponential function. Just look at that curve, shooting upwards, gaining speed. If sine and cosine are like a steady, predictable pendulum, the exponential function is like a rocket taking off. It describes things that move in one direction, either growing relentlessly or, in reverse, decaying steadily towards 0. The secret sauce, the magic property of the exponential function, is right there. Its rate of change is equal to its current size. Think about that for a second. The bigger it gets, the faster it grows. It's a feedback loop, and it's a rule that governs so many natural processes. In electrical engineering, this is the math that tells you how a capacitor charges up with electricity. It also perfectly models what engineers call a transient response. That's the little burst of activity right after you flip a switch, before the circuit settles down into its normal, steady behavior. So we've got a tool for waves and a tool for growth and decay. Pretty useful, right? But the real genius, the real power, comes when you put them together. It's time to pull out the engineer's secret weapon. And here it is, Euler's formula. Honestly, this is one of the most beautiful and profound equations in all of mathematics. What you are looking at is a bridge between 2 completely different worlds, the world of exponential growth on the left and the world of waves and oscillations on the right. So how does it do it? Well, it connects that exponential function e with our friends sine and cosine. And the key, the magic ingredient that makes the whole thing work, is that little letter I, the so-called imaginary number. For engineers, I isn't just an abstract idea. It's a tool that represents rotation. So by combining growth, E, With rotation, I, you can describe all sorts of complex behaviors, like a damped oscillation, think of a bell ringing and then slowly fading to silence. So what's the big payoff here? Well, before Euler's formula, if you wanted to figure out how a circuit would react to an AC signal, you had to solve a really nasty differential equation. But this formula gives us an absolutely incredible shortcut. An engineer can describe the input signal and the circuit itself with these complex exponentials, and then, instead of calculus, they just use simple algebra. It turns a page of difficult math into a quick, almost trivial calculation. It's a total game changer. All right, now that we have these core tools, oscillations, exponentials, and our secret weapon, we can get really ambitious. We can move beyond nice, clean, simple signals and start tackling the complex, messy signals you find in the real world. Take a look at this. It's a square wave. This is the absolute backbone of all digital electronics, the language of ones and zeros. It's definitely repeating, so it's periodic, but it is not a smooth, gentle sine wave. It's all sharp corners and straight lines. So how on earth do you analyze this with the tools we have? Well, the big breakthrough idea is called a Fourier series, and it reveals something amazing. Any repeating signal, no matter how jagged or complex, can be built by just adding together a bunch of simple sine waves. This sharp-edged square wave, it's secretly just a big sine wave, plus a smaller, faster one, plus an even smaller, even faster one, and so on off to infinity. This mind-bending idea leads us to our final and most powerful tool of all, the Laplace transform. This lets engineers jump between two different ways of looking at the exact same problem. On the left is the t-world, or the time domain. That's how we normally see things, a signal changing over time. It can be messy, the math is hard. But after the transform, on the right, we're in the s-world, the frequency domain. And over here, that messy signal becomes a simple list of its ingredients, and all that hard calculus just becomes simple algebra. Think of it like a universal translator for math problems. You feed in your tough, complicated calculus problem from the real world. The Laplace transform translates it into the frequency domain, where you can solve it easily with basic algebra. Then you just translate the simple answer back. It turns hard problems into much, much easier ones. And this all culminates in a truly incredible idea. Remember that simple expression that described the circuit? Well, this quote tells us that we can take that expression and find its roots, a few special values. And if you just plot those few points on a graph, that simple pattern of dots tells you everything you need to know about how that physical system will behave. The entire complex personality of a circuit is encoded in the location of just a few points. It's beautiful. And that brings us to the biggest takeaway of all. The math in this toolkit, it's not just for electrical circuits. These exact same equations, these same ideas, describe how buildings vibrate, how heat flows through a material, even how animal populations change over time. It seems the universe has a preferred mathematical language, and that leaves us with one final exciting question. What else is out there, just waiting to be understood, using these same elegant and powerful rules?